Hello students. So today we are going to discuss about the tips to identify oxidizing and reducing agent. In previous lecture we discussed about different oxidation states of some compounds and elements. So as we saw in that compounds, certain elements contains multiple different type of oxidation state. So these tips are mainly based on that oxidation states or different oxidation numbers. So first point is, if element is in its highest possible oxidation state, then it will act as oxidizing agent. That means if element is already on its highest possible oxidation state, no extra electrons can be released because it is already highest possible oxidation state, which represents all the electrons which are removable, they are already removed. We cannot further remove any electrons, or the elements cannot lose electrons. So if it cannot lose electrons, then there is only one possibility: it can accept electrons. If it accepts electron, it is reduction for itself and it can act as oxidizing agent. So if highest possible oxidation state is achieved, then we have only one possibility: it is oxidizing agent behavior or reduction of itself. So here we have some examples, and if we check the oxidation state, you will notice they have very high oxidation states. As for example, in KMnO4, Mn contains +7 oxidation state, K2Cr2O7 has +6 for Cr, HNO3 contains +5 for nitrogen, H2SO4 contains +6, HClO4 contains +7 for chlorines. So all the possible electrons are already removed, so there is no possibilities to lose electrons. These elements can only accept electrons, and that's why they can act as oxidizing agent. Second point is, similarly, just like oxidation, reduction is opposite process of oxidation, then similarly oxidizing agent is opposite of reducing agent and vice versa. So if for oxidizing agent behavior, highest possible oxidation states are achieved, for reducing agent behavior, we need lowest possible oxidation state. So if compound or element is in its lowest possible oxidation state, then it can act only as reducing agent. So here we have some examples which has very low oxidation state or lowest possible oxidation state. So all of these elements are not able to accept electrons because they are already on lowest possible oxidation state. That means all of the vacancies for the electrons are already occupied. These elements cannot further accept electrons. If they cannot accept electrons, that means no reduction is possible. They can only lose electrons. That means they can give us oxidation reaction of itself, and that's why they can act as reducing agents. Then our next point is, if element is in intermediate state. That means for chlorine, let's say minimum possible oxidation state is -1 and maximum possible oxidation state is +7. All the other oxidation state in between are called intermediate oxidation state. So if element is in intermediate oxidation state, that means it has possibility to increase its oxidation state or to decrease its oxidation state. That's why it can act as both oxidizing as well as reducing agent. So here we have some examples which shows intermediate oxidation state. In first example, we have -1 oxidation state for oxygen, then we have sulfur in +4 oxidation state, then nitrogen in +3, and again sulfur in +4 oxidation state. All of these are intermediate oxidation state. For oxygen, we have -2 to +2. Then for sulfur, we have -2 to +6. Then for nitrogen, we have -3 to +5. And for sulfur, as already mentioned, -2 to +6. So all of these oxidation states are intermediate oxidation state. Then next point is, if a highly electronegative element is in its highest oxidation state, not only highest but few of the highest state, then the compound can function as powerful oxidizing agent. Now, why not only highest but some of the highest? Because as we can see here, examples have some electronegative elements, highly electronegative elements, that means halogens. And not all the halogens are in their highest oxidation state, but they have some of the highest oxidation state. For chlorine, it is in +7 oxidation state. Then second chlorine contains +5 oxidation state. Then Br +5, iodine +5. So all of them has comparatively very high oxidation state, and all of these elements are electronegative elements. That means usual behavior of this element is to accept electron, and here they are showing opposite nature of it, and that's why they have strong tendency to attract electron towards them, and by attracting electrons they can decrease their oxidation state. That's why they are acting as their normal behavior. So if highly electronegative elements have their highest oxidation states, then they can act as powerful oxidizing agent. That means they will reduce itself, and that's why they will oxidize other compounds. Then next point is, if electronegative element is in lowest possible oxidation states, then it can act as powerful reducing agents if they are in their free state or in lowest oxidation state. So as we have some examples which are lowest possible oxidation state of respective ions. As we can see, iodine shows -1 oxidation state, Br -1, nitrogen -3. So these are their lowest oxidation states. So they do not have any vacancies to accept more electrons. They cannot accept electrons, that means they cannot be reduced. But they can lose electrons, that's why they can be oxidized and they will behave as reducing agents. Today's last topic is equivalent weight of oxidizing and reducing agent. We already learned about the equivalent weight or masses of some compounds based on their oxidation state. So similar thing can be used here. So equivalent weight of substance, in this case oxidant or reductant, is equal to molecular weight divided by number of electrons lost or gained. If it is oxidant, then it will gain electron. If it is reductant, then it will lost electron by 1 mole of the substance in redox reaction. So oxidation state of a compound will change during the redox reaction. So change in the oxidation state is either gained or lost electrons. If compound is reduced, then it will accept the electron and oxidation state will decrease. If compound is oxidized, then it will lose electrons and oxidation state will increase. So change in oxidation state or gained or lost number of electrons, we can use them to divide molecular weight to find equivalent weight. Now keep in mind, this change won't be negative. That means if we have, suppose we have element A which gives us A plus 3 ion, and element B which gives us, let's say, B minus 2 ions. So in this case we will take change is equal to 3, and in this case we will take change is equal to 2, not -2, because we cannot divide things with negative values, and in this case to find equivalent weight we need only difference of electrons or difference of oxidation states. So difference must be positive. So all you have to do is, whether it is oxidant or reductant doesn't matter, you have to subtract lower value of oxidation state from the higher value of oxidation state. So equivalent weight of oxidizing agent is molecular weight of the substance divided by number of electrons gained by 1 mole of one molecule, or change in oxidation number per mole. Similarly, equivalent weight of reducing agent is equal to molecular weight divided by number of electron lost by one molecule, or change in oxidation number per 1 mole. Now in both of the cases, that means in case of reducing agent as well as in oxidizing agent, change must be positive. It won't be negative.